All right. Hello, everybody. Welcome to week 4 of QDA. Feel free, as always, to put your questions and comments in the chat as we go. I know I will frequently stop talking and look at questions from chat, but also Paula and Yunhan will be able to answer questions as we go. I also wanted to do a little bit of housekeeping. I know people are maybe getting started thinking about their assignments, or at least if you're in UXD, now that you have partner groups, you have assignments on your mind. I just wanted to remind you that QDA assignments are individual assignments. They are completed on your own without sharing your writing with any of your classmates. I know I made the buddy groups for you to talk about stats concepts and to help you have someone to troubleshoot code with, but you are not meant to work together on your assignments in your buddy groups. All the written assignments, by the way, are automatically run through Brightspace's so Brightspace has like an originality checker to make sure that your work doesn't match someone else's work. So if the originality checker finds something that might potentially be copied from either something online or from another student, then the teaching team will investigate that with the UCD plagiarism policy in their hands. You can check the UCD library website for some good resources on what plagiarism is and how to make sure you are not committing plagiarism. So if you feel unsure, make sure to consult that resource or to consult us. But anyway, with that out of the way, the big week has finally arrived. It is finally the day that we can do some inferential statistics. We can test hypotheses. I know this is a big moment in your lives. You can take a moment to revel in your excitement, to pop a bottle of champagne or whatever else you want to do. This is the first class in which we will do some actual hypothesis testing. So for this lecture and for future lectures like this, we'll have an example research question, an example data set, and we'll go through the process of formulating a hypothesis, describing our data, checking assumptions about our data, and then running the appropriate statistical test, and also putting the results of that test into words so that we can communicate our findings with other people. So this week is about correlations. And to talk about correlations, we're going to use an example of social media. So maybe I talk to my friends and I notice that some people feel anxious each time that they consider posting on social media. They agonize over whether to hit the tweet button or not. You know, you type up the tweet or whatever else, and you're not sure if you should hit the button or just delete the whole thing. Others of my friend group don't experience this at all. They just anything that pops into their mind, they pop it in and hit send, and that's that. Or maybe instead of an observation, maybe it's some scientific articles that I read about this phenomenon of social media posting anxiety. Either way, either by making observations about previous literature or about making observations of the world around me, I come to this realization that this phenomenon exists, this idea of social media posting anxiety. And that observation leads me to a question, a research question. Does social media anxiety relate at all to the amount that people post on social media? So notice I'm starting with a really conservative research question. I don't know if these variables are related at all, so I'm not going to ask, does one thing cause the other thing? I don't even know if they're related, so I'm just asking, are they related? This is the broader question to get that relationship established in the first place before I try to look at what's causing what. I'm not guessing which direction the relationship might be. Like it might be that people who post more on social media feel more anxiety. Maybe that the amount of anxiety that people feel is a function of how often they make posts. So every time you hit tweet, you get a little more nervous about your next time. Or maybe it's the other way around, and that the more you tweet, the less anxiety you're going to feel. I don't have any claim about which direction this is going to go in, whether they'll both rise together or whether as one rises, the other one falls. I'm just asking, are they related at all? So this is where I kind of start with when I have this observation where I don't have a lot of other literature. I don't have a clear explanation of causality. Instead, I'm just asking, do these two variables relate to each other? So to recall my old friend, the scientific method, and this wheel diagram of the scientific method, I'm starting with an observation. I'm using that to generate a question. And before I collect any data, I need to formulate that question as a hypothesis. Only from there, from a testable hypothesis, can we start designing a study and then analyze our data to see if that hypothesis, if that statistical model about the world fits the observations that we make, if it fits the data that we collect. That'll help us come to a conclusion about whether we ought to adopt this hypothesis or not. So recall from a couple of weeks ago, we want a scientific hypothesis to be testable, specific, parsimonious, aka simple, and falsifiable. So here's how we might turn the research question we just came up with into a research hypothesis, which meets those requirements. We might say social media posting anxiety is significantly associated with the amount of tweets someone makes. I accidentally have the word on in there. Pretend you don't see that. Significantly associated with the amount of tweets somebody makes. Now, remember, our statistical tests are used to falsify a hypothesis, but this is not the hypothesis we want to falsify. We want to see if this hypothesis is correct or not, or is a good model. So we're implicitly seeking to falsify the null hypothesis. The null hypothesis might be stated like this: social media posting anxiety is not associated with, there's the word on again. Why did I do that? Is not, I think I wrote it one way and then changed the wording and then I kept the on. Social media posting anxiety is not associated with the amount of tweets someone makes. So that's my null hypothesis, that these two variables are not related at all. When we use our inferential statistic tests, today that'll be a correlation test, it's telling us how well this null hypothesis fits the data that we collected. So if the null hypothesis is a very poor fit for our data, we can reject that. And because our research hypothesis is the inverse proposition, because it's the exact opposite, if we reject the null hypothesis, that gives us support for our research hypothesis. Note, again, I'm going to really harp on this. I'm using the words associated with. These are our hints that we're using a correlation test. Correlation tests are the tests we use to detect associations between two variables or relationships between two variables. So if you see that phrase, you know you should probably be using a correlation, or if you're using a correlation, you should probably be using or seeing that phrase. You might also see, you might see related to or associated with. Either way, those are the words that go with correlation tests. Each different test will probably have a key phrase like this that I'll highlight that kind of belongs with that hypothesis, that the hypothesis that's phrased in this kind of way goes with a test like this. And yeah, for correlations, that is the phrase associated with goes with correlation tests. And somebody's already hit me with correlation is not always causation. You are absolutely right. We will definitely be harping on that point. That is a huge part of doing a correlation and a huge part of today's lecture. So note, in our hypothesis, we're specifying two variables which we want to directly measure: social media posting anxiety and number of social media posts. We can't run an experiment in which social media posting anxiety is an independent variable because we can't really assign different levels of anxiety to different people. I can't say, you have to have this much anxiety and you have to have only this much anxiety. It's an internal trait that we can't directly manipulate, so we can't really use it as an independent variable. Our other variable is social media posts. That's also a variable that we want to directly measure. I'm interested in how much someone is actually posting on social media. I'm not interested in assigning people, you should post 10 times, you should post 100 times, whatever. I'm interested in observing what they actually do. Since I have two variables that are going to be directly observed, I can use a cross-sectional design, aka an observational design. So I'm not assigning either variable, I'm just observing both variables. That means that I'll have ecologically valid data. I'll have people's real world amounts of social media posting and some measurement of their social media posting anxiety at a given moment, thus cross-sectional. I'm getting like a cross-section of the real world at a particular time.
Thursday
I didn't know if that was a question or an accidental unmute. So yeah, I'm getting ecologically valid data because I'm getting real posts, real numbers of social media posts, and real at one moment real measures of their anxiety. Remember, I'm not manipulating either variable, so I don't have an independent variable. I can't make claims about causality. I can't say that one thing is causing the other thing because I don't know whether anxiety is causing your amount of posts or your amount of posts are causing anxiety or something else is causing both. And that's fine because my hypothesis is not about causality. It's about a relationship. And that is exactly the type of analysis we're able to conduct when we have a cross-sectional design like this. Correlation studies that merely seek to detect whether two variables are related, but not whether one causes the other. Using a lot of hand gestures, that's really good for online lectures, I'm sure. So maybe I will recruit a bunch of people to take a survey which measures your amount of anxiety. And there's plenty of validated questionnaires for measuring state and trait anxiety, for measuring anxiety towards a specific behavior. These questionnaires normally come with some scoring instructions. So after a participant fills in the survey for me, after I have all of their answers, I'll have some instructions about how to add them up and get a single number score that represents their anxiety. So anyone who I ask to take that questionnaire, anyone who I recruit to be one of my participants, I'll ask them to take that questionnaire, and I'll also ask them to either tell me how many tweets they made in the past month, or maybe I can just ask for their Twitter handle and I can count them myself. So now it's a pretty lightweight design, right? It might take someone 5-10 minutes to fill out the questionnaire, and it might take me 5 minutes to check how many tweets they made in the last month. And now I have plenty of data to test this hypothesis. Now, I want to make sure I have a representative and useful sample, so I might only recruit people who use Twitter, or I might decide that people who have been diagnosed with a generalized anxiety disorder might need to be excluded from this study because I might believe that a generalized anxiety disorder might cause your social media posting anxiety to behave differently than people who don't have generalized anxiety disorders. So things like that, just to screen to make sure that my data is coming from a single population that I want it to come from. There's not the Twitter users data and the non-Twitter users, or the professional influencers and then the non-professional influencers. And by the way, if you are using a questionnaire for a variable like this, for your thesis or an independent research project or anything, most of the time, whatever variable you're interested in measuring, you can find a pretty good existing questionnaire that someone already made by looking around on Google Scholar or searching through literature about the topic you're interested in. It's almost always better to reuse questionnaires that have already been used than to make up new ones. A lot of questionnaires that you'll find have already been validated, and that takes a lot of work and data. You'll learn more about that process in research methods next term. But using someone else's validated measure means that you don't have to go through all the work of validating a questionnaire, but it also means that you can now compare your findings with other findings, that even if you're not so interested in comparing your findings and someone else's, some other researcher might want to compare your findings and someone else's. So using the same questionnaire lets that comparison be direct. And yeah, someone asked, does the second point, does high ecological validity mean that our data is real? Yeah, it means that our data is as much like the real world as possible, that it's not something that we're manipulating or causing differences in. We're kind of just taking a snapshot of the world as it exists, is the hope. So just to say this one more time and get it very clearly into your head, a correlational study does not have an independent variable. It does not have a dependent variable. It's not appropriate to refer to the variables in a correlation as IVs or DVs. A correlation test simply has two variables, two continuous variables, both of which are observed rather than manipulated by an experiment. Note that they do need to be continuous. They need to be ratio or interval data rather than categorical data. There are similar tests like a chi-square test to do the same sort of relationship comparison for categorical variables. We don't cover that in this class. You can learn more about it in the textbook, or you might, if you have other statistics backgrounds, you might have used a chi-square test before. But for correlations, which is what we'll be using here, we're using two continuous variables, two numbers. So I recruit my participants. Let's say I get 100 participants and I measure their anxiety on a standardized questionnaire from the literature. I check their Twitter accounts and see how many tweets that they've made in the last 6 months. And I visualize that relationship with a scatter plot. So my scatter plot here shows a negative linear relationship. It looks like you could draw a line that more or less describes these two variables, and it goes downward. So as anxiety increases, tweets decrease. And that's indicating to me that a correlation test might be a good test to run here, that it looks like these variables do have a linear relationship. A correlation test can give me 3 pieces of information about that relationship. It can tell me whether that relationship is positive or negative. So as one variable increases, does the other one increase or does it decrease? It can also tell me how strong that relationship is, how closely those variables are associated. Like if I drew that line, how well do they conform to that line, or are they still kind of all over the place? And finally, it also tells me how confident I can be about that data. It can tell me whether I can support or reject my null hypothesis. I gave the final outcome here, this R of 98 equals negative 0.56, P is less than 0.001. But over the next several slides, I'm going to explain each part of this. I'm going to explain what a correlation test tells us and how it works. Yeah, somebody asked, what is a negative linear relationship? So a linear relationship just means that as one variable increases, the other one either increases or decreases. You can draw a line to describe their relationship. So their relationship isn't best described by a curve or a parabola. It's best described by a line. A negative linear relationship means that that line slopes downwards, that as one variable increases, the other one decreases. Contrast that with a positive relationship, that if the line sloped upwards, it would mean that they both increase together, decrease together. So we have this idea that as anxiety scores increase, tweets decrease, or you could phrase it as tweets increase, anxiety score decreases. But now let's look at a correlation test. Let's see how we quantify this, how we test this. So what is a correlation? What exactly are we measuring here? So correlation means that two variables are related in a linear way, that they co-vary. Covariance is related to variance, which we talked about last week. It's that idea of how different you are than the mean. So covariance means that two variables differ from their own means at a consistent rate, that the extent to which one variable differs from the mean is the same as the extent to which the other variable differs from the mean. In other words, as one variable goes up, the other one either goes up or down at the same rate. For our example, as the number of tweets increased, anxiety scores of participants decreased at some consistent rate, that the pattern formed a diagonal line rather than something like a curve, that it's not like as you get really far on one extreme, then anxiety starts going back up or something, or back down. This covariance between the variables tells us that these variables are not independent from one another, that if we manipulated one of these variables, we might expect to observe some change in the other one. But it's not clear which of them is dependent on the other, or if they're both dependent on some other variable. But either way, we can expect that they would change together, that if something's influencing one, it may well influence the other as well. They're not independent. Correlations can be positive or negative, and they can have different strengths. So let's talk about first a positive correlation, and first we'll talk about a perfect positive correlation. That's the top left graph here. So a positive correlation means that as one variable increases, the other one also increases. Take, for example, the ages of two siblings. Clearly, as the age of one sibling increases, the age of the other sibling increases at a constant rate. They each are aging at a rate of 1 year per year, of course. It sounds really simple, but it's worth noting what that relationship is. This is a perfect correlation. It's a correlation with a strength of 1. Because for every data point we measure, each variable differs from the mean at exactly the same rate. They change ages at exactly the same rate each time we measure. Note that even though this is a perfect correlation, even though they're related even though they co-vary perfectly, that doesn't tell us anything about causality. That's pretty obvious that it's not my age that's causing my sister's age, or my sister's age causing my age. It's some third factor, in this case, time, that's causing both of us to age. It's causing the changes in both variables. The strength of the correlation has no bearing whatsoever on whether a causal relationship exists. Next up, in the top right, we have an imperfect positive correlation. Imperfect correlations in general are what we're almost always going to see. We're not going to see that perfect straight line. We're going to see more of a messy scatter of points that maybe a line could describe, but it couldn't describe it perfectly. In this case, we have an imperfect positive correlation, an example of the relationship between exam marks and IQ scores. For this example, they're not perfectly correlated, that plenty of other factors might impact exam marks or impact IQ scores, but there seems to be some relationship between those two variables. They increase together. We would say that this is a positive correlation because as IQ goes up, exam marks go up, or as exam marks go up, IQ score goes up. Since it's not perfect, we expect that the strength of this correlation is smaller than 1, but larger than 0, that our correlation coefficient, the measure of how strong that correlation is on this scale from 0, meaning no linear relationship at all, to 1, meaning a perfect linear relationship. Next, on the bottom left, this is a silly example for a perfect negative correlation. For me, this is the amount of money I have in my emergency chocolate fund, and it's graphed against how much chocolate I have. As my amount of chocolate that I consume increases, the amount of money I have in my emergency chocolate fund decreases at a consistent rate because I'm always buying the same chocolate bar at the same price, and I never spend that fund on anything but chocolate bars. If I manage to resist buying chocolate, I have more money. If I don't manage, I have less money at a consistent rate. This would be a correlation with a strength of -1 because it's a perfect correlation. Finally, for an imperfect negative correlation, we can take the example of rainfall at cricket matches on attendance. So as rainfall increases, attendance decreases, but it's not going to be a perfectly consistent rate. There might be some group of fans that no matter how much it rains, they're not going to leave. They're going to stay at the game no matter what. And likewise, there might be some matchups that the game is so boring anyway that attendance won't be at its max, even on a perfectly sunny day, that it doesn't matter that there's no rain whatsoever, the attendance doesn't go straight to the top. That's just the ending, so like positive, negative, positive, I don't know, probably unclear there. I think it's better demonstrated in text forms. I'm actually going to text it here. Positive. Yeah, it's just a silly way to make that shorter. I don't think that's great shorthand on my part. Anyway, the negative imperfect correlation, we would expect a correlation coefficient. We expect the strength of that relationship to be somewhere between 0 and -1. That -1 would be a perfect negative line, a perfect straight line. This isn't a perfect line. Some points are going to be above it, some are going to be below it, but it's negative, it's below 0. That direction, positive or negative, corresponds to the slope you see on the scatter plot. So an upward slope corresponds to a positive correlation, a downward slope corresponds to a negative correlation. But again, these correlations may or may not come from causal relationships. They don't come from experiments where we have a controlled variable, so we can't know whether a causal relationship exists between any of these pairs of variables. No matter how strong the correlation is, that has no bearing on whether or not we can make causal claims. So how do we get that number? How do we get our correlation coefficient? Well, we need a correlation test. When we measure correlations, we typically use one of two statistics. One is Pearson's R, named for Arl Pearson, pictured here, and the other is Spearman's rho. So when we have parametric statistics, that is to say when we have interval or ratio data that is normally distributed, we can use Pearson's R. In fact, that's the R that our beloved R programming language is named for because it's just such an important inferential statistic. Otherwise, if we don't have normally distributed data, or like if we have something that's not ratio scale, like if we have ranks like first, second, third in a race instead of race times, then we would use a different test. We would use Spearman's rho. We're not going to bother teaching Spearman's rho in this class, but you can read more about it in the textbook. So Pearson's R is what we'll be using in this class for our correlation examples. This is a test that lets us put a number on the strength of the relationship between 1 and 0, and it lets us know if that relationship is positive or negative. Also lets us see how likely it is, if the null hypothesis was true, that we would have observed the relationship between our two variables. So this is a single test that lets us get all that information, lets us completely answer our hypothesis about the relationship all in one test. I do want to make a quick note on Carl Pearson. In addition to inventing the correlation coefficient, he was also a big old racist. He was the editor of a prominent journal on eugenics and abused statistics on averages to make arguments that certain races are inferior to others. I bring that up to make two things clear. First, the people who helped establish this field were not nice people. A lot of the kind of founding fathers of statistics were similarly eugenicists and were using statistics to make pretty horrible arguments about social values. And I also want to help point this out to help you realize that the way you conduct your statistical tests, the actual statistics you do, will not be as important or impactful in the world as the way that you interpret them. Another way to say this, your discussion section is much more important than your results section. You can probably find a statistic or a statistical test to twist into any ideological point that you want to make. But the whole point of being a statistical analyst is to approach questions with an open mind and that assumptions of the null hypothesis are true, rather than assuming that your own prior beliefs, your own prejudices are true. So this is a quick way to say, don't twist statistics to make terrible arguments, or you'll be remembered the way Carl Pearson is, with the line "big old racist" put over your face in my slides. So our Pearson's R correlation test has 3 assumptions that we need to test before we can run a correlation. The first of these assumptions is that we have 2 continuous variables. This is really easy to check. Just look at your variables, think about how they were measured. Were they numbers? If so, you can pretty much use a Pearson's R correlation test. A quick note about questionnaires. It's a little bit controversial whether or not questionnaires, like Likert type questionnaires where you rate between 1 and 5, how much do you agree or disagree with this statement? It's a little controversial whether they should count as continuous variables. As a general rule, surveys that have several items that you then add together or transform to get a single score, those can be treated as interval data. That's pretty uncontroversial. What is more controversial is whether an individual Likert item ought to be treated as continuous data. We won't bother with individual single item questionnaires just to kind of sidestep that controversy. It lets us use all of our statistical tests in this class, but you may well think of other tests to use, and you can, again, consult the textbook for more info about whether or not you should treat questionnaires as continuous data. Yeah, other continuous variables might be things like age or height or reaction time or number of tweets. So it could be things that you're directly measuring in the world, like height, where you're actually getting out a tape measure, height, weight, these sorts of things. It could be things that you're counting, like numbers of tweets. It could be questionnaire data, as I said, where you add up a bunch of scores on a questionnaire and you get a single number. It's when you have a number that there's essentially that you can have any score on some interval, that it's not ranked data where everyone is at an unknown space away from one another. It's that everyone has a set unit away from each other. So whether that's each data point is measured at the level of inches, so consecutive intervals, consecutive measures on that scale would be like 1 inch or 1 centimeter away from each other. That's a continuous variable because there's some measure of how far away each point is from each other point. Whereas ranks in like a race, like first, second, or third, that's not a continuous variable because it's not clear how far away first was from second as compared to how far away second was from third. So that's our idea of continuous variables. Next, our assumption is that we have normally distributed data so that it follows a bell curve like we saw last week. In order to check this, you can make a histogram of each variable, visually inspect whether they are normally distributed. In the next couple of weeks, we'll also have a to definitively say whether or not a variable is normally distributed, that you don't just use the eye test. But the eye test is good enough, and that's what we'll use for now for the next week or two. If you fail this assumption, if you don't have normally distributed variables, or if you don't have continuous data, then you still can use Spearman's rho. You can use the non-parametric version of the correlation test. But if you meet both of those assumptions, then you can use Pearson's R. Finally, to do a correlation at all, whether Pearson's R or Spearman's rho, the relationship between our variables needs to be linear. That means it's not parabolic, it's not V-shaped, it's not shaped like some other kind of curve. To check this, we just make a scatter plot. Again, there are statistical approaches to checking this assumption, but they're pretty complicated. We don't get into them in this class. The scatter plot method's all you really need to check this, because if you're meeting the first two assumptions, then it's pretty much fine to run a correlation. The scatter plot will give you a pretty good idea whether there is some other type of relationship. If you're not sure whether there's a linear relationship or no relationship at all, then you can go ahead and use a correlation. But if you're not sure if there's a linear relationship or a parabola, and then you look at your scatter plot and see a parabola, then you ought to not bother with a correlation. And an example of where you might see like a V or a parabola. Last week, I gave the example of commute time and age. And I said that you might see very young or very old people having like a really small amount of time spent commuting per week, whereas adults between like 30 and 60 years old probably have the most time spent commuting. For that kind of data, we wouldn't really be able to run a correlation, because the correlation only lets us assess how strongly variables are related in a linear way, how well a line can describe that data. So this part of our analysis, testing these assumptions, looking at the descriptive statistics, cleaning up the data if there's any errors or outliers, that's going to take like 80% of your time and your code when running any kind of statistical analysis. The actual inferential statistic, the Pearson's R correlation test, that's going to be run in a single line of code. It's going to be really simple. It'll take about 3 seconds of thought to evaluate whether your hypothesis is supported or rejected. It actually feels pretty anticlimactic when you spend all that time getting stuff ready for this test, and then you just get your hypothesis, you get your answer spit out that quickly. But that's how simple running the test ends up being. What test would you run if there wasn't a linear relationship? So Andy Field gets into this in the textbook. I personally I haven't been hypothesizing about nonlinear relationships between variables, but if you are, you can do certain transformations to your data to either transform your expected relationship into a linear one and then use a correlation. Or I think there are other tests, but I'm not familiar with them, to be honest. I think you would see them more in the physical sciences than in social sciences. So in case you're interested in how R is calculated, you don't need to memorize this formula. I won't quiz you on this, but I included it here just in case. And the lovely program R, the software, will calculate this for you. You won't have to do it by hand. But it's perfectly easy to calculate by hand. It's perfectly possible to do with just like a basic calculator. My college stats professor used to make us calculate R by hand before he let us use R, the program, to do correlations, just to make sure we understood what it means. I'll spare you from all that, but just know that R, that number between -1 and 1, is the measure of covariance divided by the product of the standard deviation of the variables. This is, again, you don't necessarily need to know this, but this is in case you were wondering how R is calculated, how that correlation coefficient, the number between -1 and 1, is calculated. But yeah, don't worry so much about it. So our Pearson's R test will give us an output like this. For example, for our tweets and our anxiety, our correlation coefficient. Well, for our example of tweets and anxiety, our correlation coefficient, that single number, that Pearson's R, is -0.56. So it's a number between -1 and 1. I'll get to the other two parts of that in just a second, but really simply put, R equals -0.56 is the strength of our relationship and the direction of our relationship. So we know it's negative. We know that as one variable increases, the other decreases, and we know its strength. It's between 0 and 1. It's kind of right in the middle. The closer to 1 you are, the stronger of a relationship you can say that the variables have. In this case, it's a negative relationship, and it's kind of medium, not super strong, not super weak, right in the middle. Here's a little handy chart for what words you can use to describe the relationship. That a relationship between like -0.5 and -0.6, you might say it's a moderate negative relationship. This is just like a rule of thumb someone made, though. There's not like hard and fast rules of like how strong does a relationship have to be for you to call it strong, or how weak to call it weak. But generally, yeah, if it's bigger than 0.7, you can call it strong. If it's smaller than 0.3, you can call it weak. Anything in the middle there, positive or negative, just call it a moderate relationship. It's, again, this is just like a rule of thumb. This isn't like some strict rule about what words you can use to describe the relationship you observe. So the Pearson's test, as I said, gives us 3 pieces of information. It tells us the direction or the polarity of the relationship, that is to say whether it's a positive or a negative relationship. Next, it tells us how strong that relationship is on a scale of 1 to 0. So how tightly the points go around the line that describes them. That's your correlation coefficient. Finally, it tells us a p-value. So p-values are the probability of let me say this correctly because it's important. P-values are the probability of can't say it correctly. Probability of observing the data that we observed if we assume that the null hypothesis is correct. So implicitly, our test is not measuring whether our research hypothesis was correct. It's measuring whether or not the null hypothesis is supported by the data that we observed. We'll get deeper into that because this is a concept that's important for every single inferential statistic that we use. It's critical in all of null hypothesis significance testing and all of inferential statistics. The idea of p-values is super important. So let's talk about what they are, what they're measuring. So how do we make that prediction? How do we predict how likely it was that we observed what we observed given the null hypothesis? This relates back to our discussion last week of sampling distributions. So for any given statistic, if we were to sample that statistic, we would make observations of the statistic for our samples. So if we had the entire world of people for whom tweets and anxiety scores are not related, and I grabbed 6 of them, I could get the correlation coefficient for them. And I grabbed another 100 of them, and I could get a correlation coefficient for them. I'd grab 30 more, and I'd get a correlation coefficient for them. That's my sampling distribution. Here's all of my spots that R could possibly fall for that population. Now, because these are parametric statistics, because we know both of the underlying variables are normally distributed, we know that R, the correlation coefficient between them, ought to also be normally distributed. And because our null hypothesis is that the correlation coefficient is 0, we know that the mean, the place that they're going to be distributed around, will be 0 for this assumption. So that's where our null hypothesis comes in. We have a population with R of 0, and all of our samples are distributed somewhere along a normal distribution. We observed an R of negative 0.56. So we observed an R like way out here. Because we would expect all of the sample R's to be normally distributed, we can estimate how likely or unlikely it was to observe the R all the way out here, given this assumption. So with a population R of 0, it's not that unlikely if we observed an R of negative 0.1 or of positive 0.1, or even up to 0.2, 0.3, negative 0.2, 0.3. But the observation that we got, R of negative 0.56, seems pretty wild. That's pretty far from where we would expect this distribution to fall. It's actually way out here. It's a couple standard deviations away from our mean of 0. This is what a p-value is telling us. How likely was it, given this sample, given my sample size, and given the expected distribution from my null hypothesis, how likely was it that I just observed what I observed? In this case, that was really, really, really unlikely. R can put a number on that really easily, really quickly. The statistical program, can just give us a number for that really quickly, a p-value. Back in the olden days, your stats textbook might have a giant table of p-values for different statistics at different sample sizes. So you turn to your table of p-values for a sample size of 100 for the correlation coefficient. You'd go down, you'd see, okay, here's R equals negative 0.56. You'd go across and you'd say, okay, my p-value is this. Luckily, we don't have to deal with all that. The stats program R tells us. Do I mind typing that description into the text box? It's on Brightspace. So my notes are in PDF and on, I think I actually have, sorry, spoiling that he's also a big old racist. I have it somewhere in these slides, and it's on Brightspace, but also the PowerPoint version of my slides are on Brightspace, and they have my speaker's notes. So anything that I said, even if it didn't make it into a slide, can be found in text form that way. So what is a p-value in general? Let's talk about it. This might be a good text version of the explanation of a p-value. So with any test statistic, R, or any of the other stats we use in future lectures, we can think of that sampling distribution. In a world where the null hypothesis is true, we expect that the normal distribution is around that test statistic and centered on 0. So it's for that last one, we expect if the null hypothesis is true, if there's no relationship between the two variables, we have this normal distribution of possible samples centered around 0. If we conclude that our observation was very unlikely to occur due to chance because of that sample population, that lets us conclude that the most likely explanation isn't that this was some miracle. It's not that we found this one crazy sample that we got super, super unlikely and found that sample. Instead, we would say a simpler explanation is that the null hypothesis does not describe the population, that the population for whom we were sampling from is not one where the center is 0. If the center is somewhere else, we therefore can reject the null hypothesis. We can say that our sample test statistic is not from the null hypothesis population, it's from some other population. And that lets us accept the research hypothesis. Every Pearson's R distributed in a way shown in that graph, centered, most often centered around 0. So any null hypothesis is centered around 0, right? Because we're saying that we have two parametric statistics, we're saying we have two variables, whatever they are, and that they have no relationship to each other. That means for the entire population, if they have no relationship to each other, the true mean of that relationship is 0. So every sample comes from a sample of a population around 0. So this distribution is for a null Pearson's R. This is for any Pearson's R, yeah. This would be samples for some specific sample size. So it's more likely to observe a really crazy result if you have a really tiny sample, right? You might have just found like the 3 weirdos for whom there is no relationship or for whom there is this crazy relationship or whatever. But as that sample size gets bigger, you have a differently shaped distribution. But it's always, as long as we're talking about a null hypothesis, it's always centered around 0. And it's always very rare. Yeah, this is for Pearson's R. It would be rare to find a 1 or a 0. For other statistics, they might have different extremes. So next week we'll get into t-tests and t-scores. That'll have a different endings. It's not 1 and -1 as the extremes, but it's still 0 as the center. So we get our p-value, we get our percentage chance that we observed what we observed in the world where the null hypothesis is true. How do we know if it's small enough to reject our null hypothesis? So in the social sciences, we use what's called Fisher's criterion, and that's named for Sir Ronald Fisher, pictured here. We say that finding a statistically significant p-value less than 0.05, that is to say, if the thing that we observed had a less than 5% chance of being observed due to chance, if that null hypothesis was true, then we can reject that null hypothesis. This is inexact, it's arbitrary. Fisher arbitrarily picked that cutoff. There's nothing magical about 0.05 as a p-value or 5% as our cutoff. But that Fisher criterion has kind of stuck around for 100 years, and that's what we use in the social sciences. It's a pretty high bar. It's pretty unlikely that we get a false positive, that we get something that should not have counted as to reject the null hypothesis. So we set that bar, but you might also report if you had something smaller than that. So you might not only say that you had a p of less than 0.05, you might say that your p-value was less than 0.04 or less than 0.01 or less than 0.001. We're claiming in any of these cases, as long as the p-value is less than 0.05, that the chance that we observe this random sample from a population where the actual mean of the population was 0, we're saying that that is so much more unlikely than the alternative that the research hypothesis was correct, that we can then just reject the null hypothesis and instead accept our research hypothesis. There's a major issue, by the way, in social sciences about that p equals 0.05 criterion, that a study with p equals 0.049, that this had a 4.9% chance of being observed due to chance. That's treated completely differently than a study that finds a p-value of 0.051, that in one case you're accepting your research hypothesis and rejecting the null. In the other case, you can't reject the null. And this has led to some huge issues in social sciences, that tons of papers that are playing games with their data, removing certain participants or transforming the data in different ways just to force that p-value down just below 0.05 and get your paper published. That's happened a lot in the past couple of decades, and that's called p-hacking. It's led to a publication crisis where papers with significant results get published, even if they were obtained due to p-hacking, while papers with a null result, even if they were interesting, don't end up getting published, even though they would have taught us something interesting, that we had a reason for making some hypothesis, but we can't support it. That's an interesting result, but in the last several decades in social sciences, those null results have not been getting published. So if you hear about the replication crisis in the social sciences, or the problems with obsessing over p-values, you'll probably hear about that more and more in different classes for your degree. But I just wanted to allude to it now because p-values are not without their own controversy, and that 0.05 cutoff is not without its own controversy. Finally, on Ronald Fisher, I already spoiled this. He was also a big old racist. He took over that eugenics journal for Pearson after Pearson retired. Again, just a reminder that being a great statistician, inventing brilliant ways to talk about numbers, does not make you immensely qualified to put those statistics into context, to interpret those statistics. That you can interpret statistics and twist them into your own biases if you want to. It's easy to do that, and it's hard to avoid. So try not to end up like Pearson and get the big old racist label on my slides. Try to interpret your results in a neutral way, and not come to the problematic conclusions that he did. So what is a p-value? Here's a definition that you can copy and paste from my slides. One more time, a p-value is the probability of obtaining the test result at least as extreme as what you observed under the assumption that the null hypothesis is correct. This is subtly but importantly different from saying that p is the likelihood that the null hypothesis is correct. That's a different statement. That's not an accurate statement. The p-value is not a judgment of the null hypothesis. It's an estimation of how likely your data was to be observed due to chance. So when you write a p-value, you don't need to tell us exactly what number R spit out, especially if it's like a really, really tiny number like 0.000000003. Instead, just tell us if it was less than 0.001. If it's not, then tell us that it was less than 0.01. If it's not, just tell us if p was less than 0.05. If it's not any of those things, you can tell us exactly what number it was to 3 decimal places. So don't tell us p equals 0.3410432. Just tell us that p equals 0.341. Those are the general cutoffs for reporting. Some people might cut it off at a different level. You might say like p equals 0.03 or something if you had a small but not less than 0.001 p-value. But for the most part, you're either going to see one of these 3 or an exact number that's greater than 0.05. And you can say 0.05, or you can say you can have that trailing 0 or not. It doesn't matter whether you include the 0 before the decimal point or not. So as a quick reminder, correlation does not tell you anything about causation, no matter how strong that correlation is. And to make that point, these are a few correlations from the blog Spurious Correlations from tylervigen.com. It's like an old 2000s blog where some person plotted a bunch of different variables to see how well they correlate, just to point out that these things probably don't have any causal relationship at all, even if they correlate really well. Like the number of people who drown by falling into a pool correlates with the number of films that Nick Cage appears in each year at a correlation coefficient of 0.66. So that's a moderate correlation. Maybe they're causally related, but I don't have a theory as to how. Or the amount of per capita consumption of mozzarella cheese, so how much cheese people eat, as compared to how many civil engineering doctorates are awarded by each year, correlates at a rate of 0.958, 0.96. That's an almost perfect correlation. And again, I don't think it's speaking at all to a causal relationship between these variables. Or finally, the per cheese consumption with the number of people who died by becoming tangled in their bed sheets, a 0.95 correlation. Again, almost perfect correlation, no causal relationship whatsoever. In all of these cases, we can't say that one thing caused the other, or even that one thing had an effect on the other. In all of these, we can only say that they're related. We can only say that they varied together. Confounds like time or the state of the economy, other big outside variables like that probably had some causal effects on each of these statistics. And even a very, very strong correlation doesn't teach us anything about the causation or a causal relationship. Now, it might be the case that a correlation study causes us to make a new observation, and that lets us, that inspires some future research that we say, now that we've observed this correlation, we have a new hypothesis that we want to test that this thing causes the other thing. That's actually a great way to generate ideas for future research activity. So if in a class assignment for QDA, you were asked to analyze a relationship between two variables, maybe you're writing a discussion for that, it might be a good idea to think about how future work could be inspired by a causal relationship that you observed, even if, or a correlational relationship that you observed, even if even if your data, your experiment didn't show any causal relationship. You might be inspired to look into the relationship between, say, cheese consumption and PhDs in civil engineering. You might decide future work should assign a bunch of people to eat cheese and see what happens. That's a silly example, but when you observe a significant correlation and you don't know the direction of causation, it doesn't mean that you shouldn't investigate it with future work. So after a correlation test, we often then go use it to see. You often might suggest it. It might not always be done, but I would say anytime I write a paper that has a correlation in it, then in the discussion, in a lot of discussions for quantitative papers, you'll talk about what kind of future work might be inspired by the present work. And you might say, now that we know a relationship exists between these variables, it might be interesting to investigate whether that relationship is causal. And that could be looked into with an experiment like this. And you might describe the type of experiment that might test that relationship. Now, for these variables, for these silly ones, you probably couldn't think of the way to test that. You probably couldn't think of a really good way to make a useful experiment based on this causal relationship. But for something like the tweets and social media anxiety variables, maybe then you could look into a causal relationship by saying, okay, we want to rule out the idea that posting more tweets leads to less anxiety, that we want to rule out some idea of like exposure therapy to tweeting. So we're going to assign people to tweet either 10 times per week or 100 times per week and measure their anxiety. That would be maybe an okay experiment to rule out a causal relationship in one direction if you thought the causal relationship might be coming from the other one. You don't always have to do this. You don't always have to say that future work ought to look into that relationship, but for some variables, it might make sense to propose that future work. And it's always good to think about after you finish a study, what sorts of new questions does this study lead me to ask? That's kind of the impact of your work, right? Where do we go from what I just did? So it's with a correlation, even though you can't say anything about a causal relationship from that, you might be inspired to ask new causal questions based on what you observed. All right, let's sum it all up and talk about how to report a correlation. Here's how you can report a correlation in an assignment or for your thesis or for any future writing. At the end of each lecture on any statistical test, I'll have a slide like this that tells you exactly how to report it in words for a reader. This format, the exact way I'm writing these numbers, this is following a standard style. The style guide that we use for this module and for the School of ICS is the APA style guide, the American Psychological Association. So in APA style, this is exactly how to report a correlation. So first I would have a sentence that kind of describes the relationship I observed. So I have my sentence. Our study found that participants' level of anxiety was negatively related to the number of tweets they made in the last 6 months. And then I report the numbers exactly like this. On the left-hand side of my equal sign, I have the letter R in lowercase, and then in parentheses, I have the degrees of freedom. We'll talk more about what they mean next week or in future lectures, but I'll just note for now, degrees of freedom is just number of participants minus 2, or number of participants minus variables that you did not control. So for a correlation, it's n minus 2 because there are 2 variables you didn't control. So 100 minus 2 is 98. So R of 98 equals, and then on the right side of the equal sign, we have our correlation coefficient. So that negative 0.56. You could say negative 0.56 or negative 0.56. Either way is fine in APA standard. And then a comma, and then your p-value. And since my p-value was smaller than 0.001 for this correlation, I'm simply reporting it to that cutoff. I'm not saying that, I'm not doing like p equals 0.000000068 or whatever. I'm just saying p was less than 0.001. This is all reported after this sentence, so it's reported right after the sentence that helps us address our hypothesis. This really directly helps us address whether our hypothesis is supported or not. Then we put our numbers, and then we might say something like, this supports hypothesis 1. That's how you report a correlation, and this general format is how we would report any statistic. You have a statement about what you found, you have your numbers in some standard format, and then you say something like, this supports our hypothesis, or this fails to support our hypothesis, we reject hypothesis 1, or something like that. So that's how you run a correlation. That's how you report a correlation. And yeah, you can find, oh, is this the right readings? 1, 2, and 4? Is this last week's readings? And I forgot to update what our readings are. I think I might have done that. Yes, don't mind me. The actual readings are on Brightspace, and I'll tell you what they are after the break. I put the wrong readings in my slides. I think I just copied last week's slide. Yeah, so that is correlations. You'll be reading the chapter on correlations. No surprise. I guess maybe chapter 4 or 5. But I'll tell you what number chapter that is after the break. Anyway, if you have any questions about correlations or about this lecture, you can pop them into chat. If you haven't already done this, make sure you go on Brightspace and download this week's R file and this week's CSV file. There's a new CSV file called, I think it's called rtdata.csv, and there's week4.r. You can save them both in your working directory, and you can open up RStudio. And in about 10 minutes, at about 3:08, we will start the practical portion of the lecture. So I'll see you after the break. All right, hello everybody, welcome back. First, before I get RStudio open, I just wanted to point out I found the correct chapter that you need to read. It's chapter 6, the correlation chapter. Just wanted to make sure I said that like on recording, so you can't be like later on like, oh, I never read that chapter, so you can't ask about it on the test. No, yeah, chapter 6 is correlations. And you'll get to enjoy, as ever, the musings of Andy Field. He has a way with words, I'm sure you're discovering. Anyway, let's get into the R code. So hopefully everybody has their week4.r script opened up, and they have rtdata.csv in their working directory. Hopefully you've been able to set your working directory to navigate over to your working directory. And if so, if it kind of looks like this, if you have your script somewhere and you have your working directory, then we can get going. So I called it week 3, but it is week 4, but that's not even the name of my working directory anyway. And that says 2021. You might have noticed that I am stealing this code from code that I wrote last year. I have spruced a few things up, but I didn't even look in my working directory's name. So anyway, set your working directory. Anyway, your working directory is going to be named differently than mine, so it doesn't matter that I have the name wrong. I set my working directory and I import my data file. And as I said in the announcement, I'll go through these first steps. I won't rush through them. Like you can always stop me and ask questions, but I'll go through them pretty quick because these are the same steps we've been doing the last couple of weeks now. So I've imported my data. So I have RT data as a data frame over here. Since I have a new data frame, I want to look at the head and the tail. And it looks like I have 3 variables. So I have RT, that's reaction time measured in milliseconds. I have ages, and I have X, which looks to be participant number. We'll say that this data set came from an experiment where people a light would light up and they had to hit a button. And this was how quickly do people react to the light lighting up based on their age. And I know that this was a cross-sectional study. I did not manipulate anyone's age. I wouldn't know how to do that anyway. I didn't manipulate anyone's reaction time. I measured them directly. Therefore, I know that this was all cross-sectional. I know there was no dependent variable. So I don't really need this ID column. I don't need this X. We talked about last week a little bit that you might use that ID column to figure out if you had a between subjects or within subjects design to figure out whether everyone was in just one condition or whether everyone experienced all conditions, but there are no conditions. This was not an experiment. So I don't need my X column. So to get rid of a column in R, I can take that column. So I can say RT data $X. So that just means that column. And I can set it equal to null. And null is R's like fancy way of saying nothing, that you can't say 0. That would just make everyone's ID number or whatever, everyone's X, the number 0. We don't want that. We want it to be null. We want it to be gone. So when I hit that, I've set that equal to null. Now, if I do head and tail, I can see that that column's no longer there. My only 2 columns of data are reaction times and ages. That can be handy if you have like a giant data set with lots and lots of variables, but your hypothesis is only looking at like 2 particular variables. It's sometimes nice to just get rid of all the other junk so you can look at the stuff you're actually interested in. So yeah, now I have just me 2 variables, just my 2 important variables here. And I want to get some descriptive statistics for both of them. So we'll get the same descriptive statistics we did last week. You might hear my cat begging for dinner. It's not time yet, so I think she's being a little dramatic. But we'll do our same descriptive statistics as last week. That is a mean, a standard deviation, a max and a min, median, and an interquartile range. So I did them for reaction time, and you can probably already see why I do these descriptives and what might be interesting. So I noticed that this minimum reaction time was negative 35.69. That's obviously a problem because I don't want, it's impossible to have a negative reaction time, right? If somebody hit the button before the light lit up, that wasn't a reaction. It was just them hitting the button. I don't want a negative score. My actual minimum should have been 0. So I know that that negative was just improperly recorded, that there was some kind of data error. Maybe my finger slipped. I was meant to hit 135 and I hit 35 when I typed it into my data file. So I know that's erroneous data and I'll have to treat that somehow. Notice that the participant numbers are still here. So that's actually just the row numbers. So it's not necessarily participant numbers. It's just each row. Theoretically, these all could have came from the same person or something. We know that they didn't because we had that X that had everyone having a different number, but this is just the row number. So that's my descriptives for reaction time. I'll also do descriptives for age. It looks like I had a max and a min of 13 and 80, and maybe that's fine. Maybe I was not caring whether people were teenagers or adults. And yeah, it looks like my age and my reaction time both had medians that were pretty close to their means. So I'm not so worried about like a super extreme value in either ruining things. So we do need to know more about that score that was negative. It needs to be dealt with, as I put in this script. It needs to be dealt with. We need to get rid of, or we need to do something about that score that was negative. So when I looked at my head of my reaction time data, I actually saw this negative score in here. I saw that this, so I saw this negative score was the 3rd row. How do we get the RT data into the data frame? Just make sure you run this line, that you run RT data equals read.csv, and that'll get it into the environment for you. So we actually saw where that negative value comes from already. We saw that it's our 3rd data point. We saw that it's our 3rd row, and it's our first variable. It's our first column. So we can actually go right to that spot. We can ask R, what is RT data at row 3, column 1? If you use these square brackets, you can put the row number and the column number, and you can get just the value in that spot. So when I say RT of row 3, column 1, RT3, comma 1 in square brackets, it tells me negative 35.69. I also could instead, if I knew it was participant number 3, I don't have to specify row, comma, column. I could I could specify my column like this. I could say reaction time of row 3, and it tells me the exact same. Or maybe I didn't notice it in head and tail, but I still want to know where it is. I could also ask R which reaction time, which RT data $ reaction time was less than 0. So which tells me where in my row, which row number had something that fits that criteria. And it would tell me all of the values that fit that criteria. In this case, it was only row number 3 that fit that criteria of less than 0. So if I put the same, but if I put less than 100, that would tell me a bunch more row numbers, I bet. Yeah, this tells me all of these people had reaction times less than 100 because I said which reaction time is less than 100. But if I just say which reaction time is less than 0, it's telling me just row number 3. So that's my only data point that has an issue that I need to deal with. And you might find this with real data or with data that you get from other people, like in assignments, or if somebody asks you to, can you run some stats for me? You might find a data point that is impossible, and you need to deal with that. And like I said, we have good reason to believe that that was an error, that that's not like a real score, that somebody made a mistake when they typed this in. It wasn't that somebody is just like the best reaction time, the best reactor ever. We know that this is just erroneous data, so we want to get rid of it, especially because we have 200 participants. Losing one participant is not going to affect our analysis that much. So we don't really need to fret about throwing away this participant. And because we have a bad score, an erroneous score for one of their variables, and because we're wanting to do a correlation here, we can't do a correlation because we don't have any information about one of their variables. So we're just going to get rid of that participant. And the way you do that in R is you specify RT. So you specify RT data, your data frame name, and then in square brackets, a minus for the row that you want to get rid of, and then a comma with nothing after it. That means get rid of every column for row number 3. Now, I actually want to make a new data frame that has, I want to make a new data frame with a new name that has all of the same data as my other data frame, but it doesn't have row number 3. So when I do that, I make a new data frame called rtdata.clean. I could have called that anything. I could have called this like fancy data or something, made a new data frame. Either way, whatever you want to name it. Now you're saying make a new data frame that has all the same data as RT data, except for row number 3 minus row number 3. And that's what happened. So if I do head of rtdata.clean, I already see it as 199 observations, so 199 rows rather than 200. And just taking a look, that row number 3 is gone. I have row 1, row 2, row 4, but I don't have row 3. And that's exactly what I wanted. I got rid of row number 2, row number 3. So that's good. I got rid of my bad data, but maybe I don't have data that I want to throw away. Maybe there's just really valuable data in the other columns, or like I have a bunch of hypotheses and maybe I won't be able to do my correlation. So I want to get rid of them or change their data here, but I want to keep their information for the other columns. Or maybe I just have a really tiny sample size that, like, if I get rid of this participant, then I won't have any participants. In that case, I could also, instead of removing that data point, I could replace it. And I don't have a good guess about what their reaction time was, right? I have this negative score, so I have no idea what their real reaction time was. So instead of removing them, I can replace them with the mean, because remember, the mean is our best guess for everybody's reaction time. It's our best guess for that statistic. And as I've said before, the mean isn't always a great model for all of our data, but it's the best model we have. We don't have any other way to make a guess about what their reaction time was. So if I wanted to keep that participant in the data set without deleting them, I could replace their data with the mean. So now I've said mean of RT data $ reaction time. So the mean reaction time should go into RT data.replace, this new data frame that I made, row 3, column 1. So I ran that, and now I look at the head of my data, and now row 3 has just a normal a normal reaction time. I just threw the mean in there. It's not going to be a perfect estimate of what their reaction time was. I have no idea what their reaction time was, but this lets me keep that participant in the data set without deleting them. So somebody asked, how do you get rid of multiple rows of data at once? This can be done a couple of ways. So I could say, let's see, so I can mess with fancy data since that's not what I'm using for the rest of this. Fancy data is the same thing right now as RT data clean. It's just a fake data file that I'm not going to be using for the rest of this. So I'm going to go ahead and say like RT data of -3:98. And oh, that's not how that works. How do I get rid of multiples? Is it like RT data equals RT data minus C? Okay, that works. So if you use a minus and then C and then in parentheses, just whatever numbers you want to get rid of, you can get rid of multiples that way. There's some other kind of fancy ways to use R to get rid of multiple at the same time. Hopefully, you can find the proper way to do that for your particular problem. And I hear an unmute. Do we have a question? All right, I'll keep going. So yeah, I could, instead of removing that data, I could instead replace it. We replace the negative value with the mean. Won't that negative value have some effect on the mean value? That's actually a very good point. So instead of replacing with the, sorry, this was a DM, so not everyone can see this question. So the mean that I got for the entire sample was actually being influenced by that negative point. So instead of replacing with the mean, maybe instead with the mean of the entire data set, maybe instead I should say RT data, maybe I should say RT data clean equals that. And then I can say RT data dot replace is RT data dot clean. So I'm getting the mean of all of the rest of them, but not including the negative value. That way, the negative value is not impacting my mean. That way I could get an even better estimate for the mean. And you can see that this is slightly different than what my mean would have been otherwise. Kate, do you, I think it's Christine that's unmuted. If you have a question, you can go ahead or, oh, okay, sorry. I didn't know if you were trying to get my attention or not. Yeah, so if you want to replace the value that you're replacing with the mean, but you don't want that mean to be influenced by that negative value, by that wrong value, then yeah, you can first remove it and then make a new data frame that replaces that bad value with the mean of the variable from the clean data set. So that way the mean is not being influenced by your bad data, and that cleaner mean is going into your replacement. That's a good point. And the bigger that your sample size is, the less that would matter, but it's still definitely worth saying that the more extreme that value is, if it was like -1 billion, then that would have messed up my entire data set if I didn't remove it first. So that's a great point to remove it before replacing it. This is, sorry, I'm getting into like these really technical questions, but I'm a bit confused. How do you guys say the new file fancy data into the environment? So to get anything into the environment, you have to run that line. So if I want, let's say I want a new data frame called Justin's data equals RT data. If I want Justin's data in the data frame, it doesn't go there if I just put it in my script. My script is just a notebook. I have to run that line. Once I run it, it appears in my environment. But before I run that, it won't do anything. You have to run a line to get it to go into your environment. So when I run it, it hops right down into the console and makes that happen. Bad data gets replaced by the mean value. Will have any effect on the overall mean? So yeah, if you remove the bad data first before you replace the mean, then that bad data isn't impacting the mean. So that was a really good point by Ashray to say that we should probably remove it before we do the replacing. So anyway, so we've replaced or removed that data point. We're going to stick with removing it because we don't think the mean is going to be a good idea. Someone asks, does pressing run do the same thing as copying the data manually into the console? Yeah, it does. So if I hit run on this line, it copies that exact line right into the console and runs it. So run is a quicker way to do that. So when we're running our own code, should we write it in the console box or in the box above? I always write all of my code in the script. That's basically your notepad, so you can save it for later. So if you write it all in your script in your .r file and save it as a text file, then you have it, and you can run it right from the script. It doesn't hurt you to have it up here. Where if you do some important if you write some important piece of code down here in your console, then later you won't have that saved, right? So just as a good kind of habit, write your code in the script and then run it down to the console. But if you're, a real daredevil, if you really want to live on the edge, and I have a bad habit of doing this, you can do all of your R work right in the console and not ever have it saved anywhere. The problem comes like tomorrow or next week when you're like, where's that great formula that I ran to clean all this data before I do a correlation? Then you're like, I wrote it in the console, it's all gone. That's why writing it in the script is a good idea. So we've cleaned up our data set a little bit. We've removed that bad data point. So we're going to work with rtdata.clean. So this one with 199 rows rather than 200 rows. And I'm glad to hear, Kaylee, that you're at least back on your feet if a bit behind. So hopefully the notes can help guide you up to where we're at. So we're going to work with rtdata.clean, 199 rows. We've removed the negative data point, or the impossible data point, the one with a negative reaction time. And now we want to get a histogram of both reaction time and of age. So first, I observed earlier when I did the max and min and all that, my max for my reaction time was just above 600. And I know that the actual minimum for reaction times was 0. So I'm going to define those breaks like I did last week, and I'll put my breaks every 100 from 0 to 600. So I can get a look at this distribution. And for reaction time, just looking at it, I didn't do the biggest breaks. Maybe I should have done every 50 or something. But that looks like a bell curve to me. It looks like it's mostly centered on this median and slopes down on each side. It's not obviously not a bell curve. That's a really confusing way to say that. I'm not looking at this and like really alarmed by it. I'm maybe a little bit suspicious, but I'm not so alarmed by it that I think I can't run a correlation. And again, in next week and in future weeks, we will have an actual test, so you don't have to eyeball it and go with your heart. You can just go with a number. But for now, we're going to eyeball it. We're going to say, yeah, that looks normal enough. So we also want a box plot of our data. I think I did RT replace here, but I should have done RT clean. And it looks like from our cleaned data, we have a pretty equal-sided box plot. It doesn't look like we're skewed in either direction. And we only have this one point that might possibly be an outlier. There's this, so when the box plot draws a circle past the whisker, the box plot is claiming that this is an outlier. But as you've probably read now in Andy Field's book, this isn't really our statistical definition of an outlier. The box plot's using the interquartile range to draw these whiskers. So anything beyond 1.5 times the interquartile range is going to get classified as an outlier. But we normally consider about 2 or 3 standard deviations from the mean as an outlier. So you can use either of those standards, 2 standard deviations from the mean or 3 standard deviations from the mean. But whichever one you use, you should be explaining it to your reader that either I identified an outlier that was more than 2 standard deviations from the mean, or you might say we did not identify any outliers, and then in parentheses, points more than 3 standard deviations from the mean. Whatever standard you're using, just communicate that and communicate whether you found them or not. In histogram, if we have to represent something on both X and Y axis, how do we write that in R? So you can only plot one variable at a time in a histogram. So my histogram up here was for reaction time. I will get to one later about age. Nope, I didn't make one about age. So I'll make one right now about age. You have to do each variable on its own. You can't do a single histogram for both. We'll say 0, 10, 20, 30, 40, 50, 60, 70, 80. So RT of age. Oh, I mistyped one. There we go. There's my histogram of age. So we would need to do each variable independently. We can't do one histogram for both. But my histogram of age also looks completely fine. And my box plot of age looks there's a few people right beyond the whisker. I don't get into it in this script, but I don't think any of them ended up being actual outliers more than 2 or 3 standard deviations. But let's talk about this one potential outlier from the reaction time data, this person that's above 600 milliseconds. So we might want to look into that. We should treat that outlier just like we treated bad data earlier. But for the purpose of this demonstration, we're going to leave it alone for right now. First, let's get a scatter plot going to see. So our assumptions for our correlation are that we have continuous variables. So we do age and reaction time. That we have normally distributed variables, and we do. We just checked our histograms, and we have these nice bell curves for both. And our last assumption is that we have a linear relationship. And the way we test that is just making a scatter plot. And like I said in the lecture, what we're really looking out for here is that there shouldn't obviously be some other relationship. So as long as we're not obviously seeing some like parabola or V shape or something other than a line, then we can go ahead and try to do a correlation. If we did see something that clearly was not a linear relationship, then we wouldn't want to bother. But since this, you're looking at it and you're like, maybe there's a straight line that there's like a slight positive correlation or maybe a slight negative or something. You're not sure that there's a linear relationship, then you can go ahead and run a correlation to check. From our 199 data points, it looks like there's no clear linear relationship between age and reaction time, but there's no clear other kind of relationship, so we can check that with a correlation. So let's talk about that outlier, that person with a reaction time up above 600. Like I said, we actually define an outlier as something that's the mean plus, and I'm going to go with the standard of 3 standard deviations away from the mean. That's what we often go with in statistics. You can, again, see in the textbook, Andy Field talks about some people go with 2, some go with 3. You have to make this decision for yourself. You have to explain which decision you made. But if you say that I was looking for outliers that were more than 3 standard deviations from the mean, then you're establishing for your reader, here's what my cutoff was, here's what I did with data that was beyond that cutoff. So I can ask R, which of my data points was my max? So I should actually, I keep saying replace here, but I think I actually wanted to use, we'll just use the replace, whatever. This is the one where we replace the negative value with the mean instead of the one where we removed it. So we're asking R, which of our data points for reaction time is equal to the max of our data points for reaction time. And notice if I'm using the phrase is equal to, I use 2 equal signs. Just using 1 equal sign is like when we're setting a variable, that's telling R, make this thing equal to that thing. When we're using 2 equal signs, we're asking R, are these 2 things equal to each other? Equals equals. Hopefully that weird pronunciation of equals equals will help you remember that 2 equals is a question. So which is the max? Which is the one that is above 600? And R is telling us that is row 2, reaction time of our second participant was above 600. So now we can just replace that point with the mean plus 3 standard deviations so that it's very high, but it's not an outlier. So now instead of using the mean for replacement, we're using the cutoff of outliers. We're retaining a lot of information about that point. So if we replace it with a mean, we're removing a lot of real information. We would drop it all the way down to here, which doesn't really reflect that this person had a high score. If we instead just drop it to the point where they are 3 standard deviations above the mean, then that means we're not deleting that information. We're not deleting the information that they were a high score. We're just replacing it with a high score that won't bias our statistical test. We might also first check, so what was our mean for, excuse me, sir? Say, what was our mean for that? Our mean was 261, and what was 3 times the standard deviation of that? So we already see that 3 times the standard deviation of reaction time, adding that to the mean, that's going to be about 561, where we know that this person's above 600. So we know replacing them with 561 is going to lower their score just a little bit, but it'll still mean that they are the highest score that we have. So we are going to go ahead and do that. We're going to say RT-data.replace, and we're replacing row 2, the second person, because R already told us that row 2 is that max. Column 1, because reaction time is our first column. We're putting that on the left side of our equal sign, and it's just one equal sign because we want that point to be equal to the mean plus 3 standard deviations of reaction time. So we did that, and we can run another box plot. And now with that point replaced by a high value, we don't have any outliers. So we're all good. We don't have any outliers. We're normally distributed. We can go ahead and run our correlation test. This does alter the data, definitely. So you're forced to make a decision as a statistical analysis. You're forced to make the decision of whether you are running a bigger risk of altering your data and reporting some effect that wasn't really there, like creating some false positive, or if it's a bigger risk that your outliers will mask some effect that was there and you won't see that effect because the outliers were there. So that's a false negative. And you have to weigh that up as a data analyst. What my argument would be for this is that we had just one outlier and it was just a little bit above the point where we would consider it an outlier. So it might monkey with our statistics a little bit if we don't replace it. It might make us not detect a relationship that's really there. But replacing it by a value that's just a tiny bit smaller isn't going to change the direction of that correlation or the strength of that correlation. But it might make it it might not influence it so badly that we don't detect it whatsoever. If we had like lots of outliers, if half of our data points were outliers, we would probably say we just have bad data. We can't run a statistical analysis for these. Or we might, Andy Field gets into this, we might run like a trimmed test where we only take like the interquartile range and do a correlation of them. Yeah, in a lot of cases, it's better to just remove the outlier. It really depends on the sacrifice you want to make. That if you want to keep that person's data because you think there might be some important information there that, let's say this person's data was, maybe they had a really high score for age and a really high score for reaction time that was an outlier on just one of those variables. In that case, getting rid of that data point gets rid of a major indicator of your correlation, right? It's someone who varied from both means in the same direction by a lot. If you get rid of that data point, you might say that there is no relationship at all, even though that data point really helps you know that there is a relationship. In that case, removing the outlier doesn't help you. It actually harms you. It makes the relationship that actually was there in your data get masked by the fact that you removed them. If instead you just scooch them down a little bit so they weren't an outlier, then you might still be able to observe that relationship. You're still capturing the data of that participant without biasing your statistical tests. But it's something you have to weigh up as a statistical analyst even. In the case of bad data, in the case of like obvious errors in the data, like a negative score for reaction time, I would probably remove that because I think that there's not any information there for me to use. On the other hand, for something like an outlier, especially an outlier that it's my only outlier, it's only an outlier by a tiny bit. In that case, I think it probably does have information that I want to keep. And in that case, I'd probably replace it by an extreme score. In general, if I don't have many outliers, I replace them with extreme scores rather than removing them, just because just because someone is an outlier doesn't mean that their data isn't real, right? It doesn't mean that they're not part of your sample. And that kind of gets at the question I got as a DM. Someone asked, how many outliers should we remove if there are many? I think Andy Field might have a rule of thumb where it's something like you don't want any more than like 5% of your data to be outliers. That if you're replacing like 5% of your data, you have a big problem. But if you're replacing a few data points and you have a bunch of them, you should probably seek to replace them rather than remove them, just to preserve as much data as you can. Because like data, it's important to reflect what your actual sample looked like. You don't want to remove people from that sample just because you don't like their score, basically. But also it's costly, right? If you had a sample of 20 and you paid if you paid each participant like $500 to complete your study, or 500 euros, you probably don't want to remove like 5% of your data just because of an outlier. You might instead seek to transform that data, seek to still use that data, but replace it with a less extreme value, just because you don't want to throw away data that costs you 500 euros. That's a silly example. In this test, in this experiment, maybe I had everyone work for like 3 minutes, so all they got was like €1 or something. And I had 200 participants. I might say, I had 200 participants. I'm not losing anything by removing that data point, so I'm going to go ahead and remove it. That's all part of your part of what you're weighing up when you're deciding whether to replace or remove a data point. And the decision is up to you as the analyst. And that's something that you have to explain to your reader, that I decided to replace this data point with an extreme value because I wanted to preserve the information about how high their reaction time was. Or I decided to remove this data point because it was an outlier and I have 200 data points. So I don't believe that. It's unlikely that removal of this point will cause a false negative, will cause a type 2 error. Explaining not only what decision you made, but why you made it to your reader is transparent. It's helping explain the statistics that you ran. So there's not like a right or wrong answer for how to treat your outliers or how to treat your erroneous data, how to treat your bad data. But whatever choice you make, you should have some reason for making that choice, and you should communicate that decision making. You should communicate your reason to the reader. And I'm saying it pretty vaguely, but I'll say it really directly. For your assignments, you'll have to make decisions like this. And us as graders, we don't care which decision you make. We just care that you have some reasoning and you communicate that reasoning to us. And that's true when I am reviewing journal articles or papers that people submit to conferences, that I don't necessarily care what decision they made with their data, but I care that they can explain it to me and that their reasoning makes sense. So that's how you make that decision, and that's how you kind of weigh up your options, but also communicate the options you were weighing up. But anyway, we did all of that. We did our scatter plot. We tested all of our assumptions. We cleaned up our data. We replaced an outlier with an extreme value. We removed we maybe did mean imputation, where we replaced a bad data point, an erroneous data point with a mean, or maybe we did removal. Maybe we removed a data point. Either way, we did all this like cleaning and checking our assumptions and all this, and we can finally do our correlation. And after all this code, you're probably worried like, oh man, the correlation is probably going to be a real pain to run. It is not. This is like the simplest part of the entire R file, I'd say. It's just core.test. That's the formula to run a correlation. And then in parentheses, first one of the variables you want to correlate. So rtdata.replace $age, comma, the other variable, rtdata.replace $rt. And you can do them in either order. It doesn't matter which one you put first or second. You just put both variables separated by a comma inside the parentheses, run core.test, and you get an output like this. So I got blah, 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 a bunch of information. The very last thing that you get here is your correlation coefficient. That is your R number. So I would write it up like this. I had 200 participants. I had two variables. So 200 minus 2 is 198. R of 198 equals negative 0.13. So that's my correlation coefficient. And I got a p-value. My p-value was 0.075776. I simplified that to 0.076. So I'm saying that age was not significantly related to reaction time. R of that equals that, P equals that. I also wanted to just draw to your attention, but you don't have to report confidence intervals. You should probably avoid reporting a confidence interval unless you're confident you can do it to APA standard. I can teach you how to do them at some other time, but I don't really expect to see them in the assignments. You won't see them all that often in published work, though maybe you should. They might be a better option than a p-value. But the correlation test gives us a confidence interval, a 95% confidence interval. It's saying that we have 95% confidence that the correlation, or that the actual correlation coefficient between these variables for the population is somewhere between minus 0.62 and positive 0.013. So one thing you'll notice, our 95% confidence interval, we're 95% confident it's within this big wide range, but that range might include either positive or negative scores. We're not even sure which direction these correlate. That goes hand in hand with not having a statistically significant result, with not having a p-value less than 0.05, that we think there's a greater than 5% chance that we would have observed what we observed if the null hypothesis is true, if the true population correlation coefficient is 0. So that's reflected in our confidence interval. 0 is within that interval. We can't rule out that there is just 0 relationship between these variables. So our hypothesis that age and reaction time are correlated or are associated, that cannot be accepted. We reject our research hypothesis. We accept the null hypothesis in this case. So yeah, that's all the work you have to do leading up to a correlation test. And then the one simple line that gives you all that information of the correlation test, your correlation coefficient, your p-value, and your degrees of freedom, which let you report correlation to APA standard, and it lets you say something about your hypothesis. So our study found that participants' age was not significantly related to their reaction time. R of 198 equals negative 0.13, p equals 0.076, and our hypothesis was rejected, something like that. But yeah, that's the end of this lecture. I know I tried to cover a lot and answer a lot of questions, but I hope that didn't put everyone on the back foot. I hope the recorded nature of the lecture, plus all of the feedback from Yunhan and Paula in the chat, plus all of the notes in the R script can hopefully help you sort through how to do a correlation. But if you have further questions, please let us know. Please ask your buddy groups. Please email us. Please use the different resources like the textbook or Stats Exchange or anything like that. Come to office hours. We're happy to talk more about this in general. That's pretty much it. Oh yeah, Yunhan is dropping facts about sampling distributions. Yeah, if you have a normal distribution, 1 standard deviation away is a 0.68% chance of occurring. That is 68% of your data falls within one standard deviation. 95% of your data falls within 2 standard deviations. 99.7 falls within 3 standard deviations. So that's how the p-values are doing that. They're going, you have your normal distribution for your null, and you're getting 1, 2, 3 standard deviations away, 2 standard deviations away to get your 95% cutoff, maybe even another one to get your less than 0.001 cutoff. But yeah, that's it for correlations. That's it for this week. Yeah, I'll stick around for some questions in chat. If our correlation is weak, like 0.13, but our p-value is strong, do we still report that there was a relationship? It's just weak? Yeah. So if your p-value was less than 0.05, sorry, if you had a statistically significant result, but your correlation coefficient was weak, you would still report that. You would say there is a weak negative relationship between age and reaction time, and then you would report your numbers. So you would only say that it was weak, moderate, or strong if you had a significant relationship. Otherwise, you would say you didn't detect any linear relationship. But as long as that p-value is less than 0.05, then you can report that there is a relationship. And you would just, yeah, use a word like weak to describe it if it's that small. Can we get the procedure? Yeah, that's a good question. I'll have an assignment review lecture in a couple of weeks before the assignment is due. But the procedure, the methods, the introduction, the related works, you are living in a world where you can pretend that that was already written for the assignments, that the data in your assignment is handed down to you from somebody who already did all of the not only that did they run the experiment, but they wrote up all of the procedure and methods and all that for you. So you don't need to tell me anything about the methods because that's already written in this imaginary world, right? That we're saying that the procedure is already somewhere else in the paper. I'm just reading your assignment, which is just the results and the discussion. So you don't really need to know where the data comes from because that was already explained up in the methods. So now you're just telling me about the results that you found, so your statistical analyses and the discussion, the putting that analysis into context, into the broader context of the literature. So good question. Where do we find that procedure for the assignment? It doesn't exist, but you can imagine that someone wrote like the perfect introduction related works and methods section already. So the procedure is written just in the mind. Yeah, I'll in the review section before the assignment. I think that's week 7, maybe week 6. I will show an example of a past assignment that's based on a different question, and that will show how you go about writing up a results section and a discussion section. Is a 5-point Likert scale continuous? Can we throw it into the core.test? I'll answer the second question with for the purposes of this class, yes. The first half of that question, is a Likert scale continuous? It's a big debate in the social sciences. For this class, we treat it as if it is. We actually treat entire questionnaires as if they are. That is to say, if you have a bunch of Likert items, like 5-point scale items, and add them all together and use them for one questionnaire, that total score is continuous. Is each item continuous? Maybe, maybe not. I don't really want to wade into it. I can post on Brightspace some of the discussion on whether or not we should think of those things as continuous. But for the purposes of this class and for the purposes of your degree, we treat them as continuous. You might later on in a grad program run into a supervisor who's like, what? You can't use inferential statistics on those. Those aren't continuous. People fall on different sides of this debate. It's more of a philosophical question than a purely mathematical one. What analysis do we have to do? That is the whole assignment, so I can't tell you that. I will tell you what the hypothesis is, and you have to do an analysis that addresses that hypothesis. That is the analysis you'll be doing for the results section, where you'll describe things like what data cleaning steps you went through, things like what the descriptive statistics were, and then things like what inferential statistic test or tests you ran. The online test is the last week of term. I have Brightspace open, so I can check that. That is visible to me, but not visible to you. So I can quickly check what date I have that scheduled. It is tentatively scheduled for December 1st. That is a Thursday, so we would be meeting anyway, and it would be open for 24 hours, but I will give you the password for the online test. I give you the password in our class meeting time, and then anytime within the next 24 hours, you can open the test and you have 1 hour to take it. So you can like come pick up the password and then like, go hop yourself up on energy drinks and then take it. Yeah, it's a 10-question multiple choice test. So the hour, when we used to do this class with many fewer people in person, in person, almost no one took the full hour. Some people did. I mean, I think they just took it to like really just reread and agonize over each question again and again. But you won't feel pressed for time. You'll more feel pressed for like, is it that answer or both of those answers? But you won't feel pressed for time. It's 1 hour to do 10 multiple choice questions. Alrighty, so that's it for QDA. I'll see you right back here next week, same time, same Zoom link. And yeah, feel free to keep asking us any questions or getting any feedback you need. And we don't know things such as methods working, get the material to study regarding the assignments. So for each of the assignments, I have posted a number of related papers that you might want to read. These papers are related both in the sense that you might want to cite them in your discussion, and you might want to cite papers that they cite or that cite them. But you also might want to use those as inspiration for what a quantitative research paper looks like, or for at least what the results and discussion section of a quantitative research paper looks like. Otherwise, you can also just look up any of the papers that like me or that some of your lecturers have written. So things like people like Dr. Cowan, Ben, people like Yunhan, people like Paula, Susan Levy, Marguerite Barry. These are all lecturers in ICS who write papers that are sometimes quantitative. So just find quantitative papers and look at how the results and discussion sections are formatted. And that's a good way to study for the assignment, so to speak. Find well-written quantitative papers and read them. I specifically mentioned me and Ben and Yunhan and Paula because if you learn to write like us and format papers like us, and then we are the ones grading your paper, we're probably going to be like, man, you write in a really good style. I really like the way you write, because inevitably we like the way that we write. You can find papers that are written by us by typing our names into Google Scholar. That's probably the best way. But also for the assignments, you can just go to the actual assignment for assessment 1, and you'll see that I provided a couple of references. So I already forget what references I gave. So I'm opening it on Brightspace on my other monitor right now. Let's see, edit assignment. And yeah, you are dismissed. Like if you're not sticking around for questions, you don't have to hang around for this. Don't worry about hanging out if you're rushing off to something else. So I give a couple of references, including SUS, a quick and dirty usability scale. I use Hart and Stavlin, NASA TLX. That's a good quantitative paper. I do Hart, NASA task load index 20 years later. That's not so quantitative. It's more just some thoughts. I include Longo and Diondo on the relationship between perceptions of usability and subjective mental workload. That's probably a really good paper to look at how it's written if I included it in the references there. That's because I think it has a strong results and discussion section that you can help model off of, and an even stronger paper, Wu, Edwards, and colleagues, 2020, mental workload and language production in non-native speaker IPA interactions. This was a quantitative paper me and Yunhan wrote. So this is like really, really the paper you should be looking at to model how to write a results in a discussion section, because that's like most of the teaching team was involved in writing it. This is like your number one place to look for, like, okay, here's how I report what data cleaning I did, what my inferential statistics told me, whether my hypothesis was supported, and then I move on to my next hypothesis, or then I get out of there. Yeah, modeling your writing on our writing will make us think that your writing is good, is my general advice. Yeah, I also have on the Brightspace discussions somewhere some resources about writing quantitative articles. I also have in the assignments folder in my learning under assignment 1, I have the APA paper guideline thingy. What do I call it? APA template. So this was a template that my undergraduate advisor wrote up that teaches you how to write each section of a paper. So look over how he teaches to write a results in a discussion section, and that should help too. But yeah, the more examples you can get of quantitative papers and just modeling your writing on how they write a results in a discussion section, the better. Yeah, the more it looks like published work, the better. Alrighty, I'm at my limit. I have 1 minute left that I'm on the clock. Then I don't get paid to take these questions, so you'll have to email me. Good seeing you all, and I'll see you all next week.